Welcome. This video is about the complex representation of the Fourier series using complex exponential functions. So given a function f of t, and this has the property that it is 2π periodic. For sake of simplicity, for sure you can also use a general period capital T. So, and if you have a 2π periodic function, you can represent it as a Fourier series. So we recall here is the DC component plus an infinite sum from the fundamental frequencies up to infinity of AK Fourier coefficient, the even function cosine kt, all the harmonic and nth harmonic frequencies, plus bk sine kt. So these are the odd functions, also the fundamental frequency for k equal 1, double frequency, triple frequency, and so on. Recall also that you can only write the equal sign for points where ft is continuous. At discontinuous points, the Fourier series, so series up to infinity, converges to the average of the left hand and the right hand limits of the function. So now we want to represent the entire expression using complex exponential functions. And therefore, we recall the famous Euler formula. So here on the right side, I continue e power I phi is the cosine of phi plus I sine phi. There is also another version. You can plug in the negative angle. As cosine is even, the negative sign doesn't matter. And as sine is odd, the negative sign you can pull out. So we simply add these two equations on the left side. On the right side, we get 2 times cosine of phi. The sign vanishes. And we also subtract and if you subtract it, you get minus minus is a plus, so 2I sine phi. So from these two equations, we get representation for the cosine of phi in terms of exponential functions. So it is 1/2 e power I phi plus e power minus I phi. And analogously, the same for the sine phi. Actually, you have here 1 divided by 2i, but 1 divided by I is minus I, so I directly write minus I half. Fine. So we use these two formulas now in our Fourier formula, but you have to substitute the angle phi with k times t here twice. So, and we get the following. The DC component remains the same. The summation is from 1 to infinity is also the same. And then we have here 1/2 AK and the term for the cosine. So this is e power I kt instead of the phi kt, and plus the same with the minus sign. And then we have minus I half, the bk coefficient times the same with minus. Close the square bracket. So now we rearrange the terms. So the sum remains. And now I'm identifying the terms that contain e power IKT. So here and here. And then factoring out also this e power IKT. And this yields the following. So 1/2 AK minus 1/2 times I BK from the second coefficient, and e power IKT factored out, plus, I'm not sure if there is enough space, probably I write it below. So I have also split the sum. Now I write the terms with e power minus IKT in a separate sum. That is, I split the sum into two separate sums, and we get the following. We have 1/2 AK plus 1/2 I BK e power minus IKT. And there we go already. We can call this as the coefficient CK. And if you compare it here, this turns out to be C minus K. So we will come back to this in a few minutes. And the DC component turns out to be C0. Great. In order to understand this here, we need to calculate the constant CK. So the first one was a definition, yeah. So this we defined here. And I just copy. Factor out the 1/2. So we have AK minus I BK. And now we plug in the Fourier coefficients, which means is 1/2. And then the coefficient, the formula for the first one is 1/pi. Period is 2pi. And the AK are responsible for the even parts, so it is the cosine KT dt. And then we also have the second term here, so we have minus 1/2 times I 1/pi integral from 0 to full period 2pi, and the BKs are for the odd parts, so we multiply by the sine KT dt. And now we write everything under one integral, so it is 1/2pi times the integral over the full period once again, and now ft is factored out, and what remains inside is the cosine of kt minus I, don't forget the I in front of the integral, minus I times sine kt. So that you clearly see this is a negative sign. Okay, and we need to integrate it according to integration variable dt. So now we can write it in a simpler form, because what do we have here? This cosine kt minus I times sine kt. I can use Euler's formula once again, the corresponding one with the negative sign, so it was the second one here. So I can represent it again in terms of an e function. So this one is then e power minus IKT. I move it upwards that you can see. So we have now found a formula for these CKs. So, and before I said that the second sum here is for constant C minus K. This derivation of the formula is nearly identical. Just replace the minus signs with the plus signs and you will get at the end. So probably I do it and then delete it afterwards. So here there is a plus. Then here we also have a plus. Here there is a plus. And then you have e power plus IKT. So this means it's actually the same as the previous formula, but you use here a minus k. So you essentially get the same formula just with k replaced by minus k. In other words, this is simply c minus k. So I remove the minus once again. Good. For k equals 0, we have to do a separate calculation here now. So hopefully here is enough space. I write here C0. What is now C0 according to the CK formula? 1 over 2 pi integration from 0 to 2 pi ft. But then you have e power minus I 0t. So e power 0, which is simply 1. I don't write it now. And what is this? This is actually our A0 divided by 2. This is the DC component. So you also see that this corresponds to the mean. So this helps us to write down this Fourier series in a very simple form. So we sum. The first sum actually is CK times e power IKT. So this is the first sum from k equal 1 to infinity. Now I can also include for k equals 0. So I start here. Instead of k equal 1, I can start from k equal 0. So let's delete this one. And we also include for k equals 0. And the other infinite sum here sums the minus k. So it actually goes into the negative direction. If you plug in 1, you have c minus 1, e power minus I t. K equal 2, c minus 2, e power minus I 2t. So you can simply include it in this infinite sum and say, I start here from minus infinity. And then I cover both sums. Because here you start from k minus infinity, go to minus 2, minus 1, 0, 1, 2. And as I explained now before, the value for minus 1 is here, c minus 1, e power I minus 1t. Everything fine. So this is a summation over all integers. And I rewrite it once again. What are my CKs? 1 over 2 pi integration from 0 to 2 pi ft e power minus IKT dt. So these are our final formulas. The first infinite summation over all k. So k are from integers, is this infinite sum from minus infinity to infinity. And note here it is e power IKT. And the Fourier coefficients, the complex ones, can be computed like here. 1 divided by the period integration over the whole period times e power minus AKT. So do not mix up this, it's better to look it up, not to introduce an error. So, to sum up, the complex form of the Fourier series, as you can see here, uses the complex exponential function along with the coefficient ck. These coefficients indicate the importance of each frequency omega is equal k, the ck's here. The larger the magnitude of ck, you know ck is probably a complex valued number, so you need to compute the magnitude in order to see. The larger the magnitude of ck, the more significant that frequency is. If the magnitude of the ck is small, that frequency plays a minor role. That's it for now. Thanks for watching and see you next time.